Great. So welcome back to the class. We are starting a very exciting new topic for which we have been building up from the beginning of the course. So today we are going to talk about deep learning for graphs and in particular techniques around graph neural networks. And this will be one of the most central topics of the class. And we are going to spend the next 2 weeks discussing this and going deeper into this exciting topic. So the way we think of this is the following. So far we have been talking about node embeddings, where our intuition was to map nodes of the graph into d-dimensional embeddings such that nodes similar in the graph are embedded close together. And our goal was to learn this function f that takes in a graph and gives us the positions, the embeddings of individual nodes. And the way we thought about this is we thought about this in this encoder-decoder framework, where we said that we want the similarity of nodes in the network, denoted as here, to be similar or to match the similarity of the nodes in the embedding space. And here by similarity, we could measure distance. There are many types of distances you can quantify. One type of a distance that we were interested in was a cosine distance, a dot product. So we say that the dot product of the embeddings of the nodes has to match the notion of similarity of them in the network. So the goal was that given an input network, I want to encode the nodes by computing their embeddings such that if nodes are similar in the network, they are similar in the embedding space as well. So their similarity is high. And of course, when we talked about this, we were defining about what does it mean to be similar and what does it mean to encode. And as I mentioned, there are two key components in this node embedding framework that we talked to in the class so far. So our goal was to map each node to a low-dimensional vector, and we want to encode the embedding of a node in this vector ZV. And this is a d-dimensional embedding, so a vector of d numbers. And we also needed to specify the similarity function that specifies how the relationships in the vector space map to the relationships in the original network, right? So we said, this is the similarity defined in terms of the network. This is the similarity defined in terms of the embedding space, and this similarity computation in the embedding space, we can call this a decoder. So our goal was to encode the coordinates so that when we decode them, they decode the similarity in the network. So far we talked about what is called shallow encodings, which is the simplest approach to learning an encoder, which is that basically encoder is just an embedding lookup. Which means we said we are going to learn this matrix Z, where every node will have a column reserved in this matrix, and the way we are going to decode the embedding of a given node will simply be to basically look at the appropriate column of this matrix and say, here is where its embedding is stored. So this is what we mean by shallow, because basically we are just memorizing the embedding of every node, or we are directly determining the embedding of every node. So what are some of the limitations of the approaches like deep walk or node to vec that we have talked about so far that apply this shallow approach to learning node embeddings? First is that this is extremely expensive in terms of the number of parameters that are needed, right? The number of parameters that the model has, the number of variables it has to learn is proportional to the number of nodes in the network. It is basically d times number of nodes. The reason for this being is that for every node, we have to determine or learn d parameters, d values that determine its embedding. So this means that for huge graphs, the parameter space will be giant. There is no parameter sharing between the nodes. In some sense, every node has to determine its own unique embedding, so there is a lot of computation that we need to do. Then this is what is called transductive. This means that in transductive learning, we can only make predictions over the examples that we have actually seen during training phase. So this means in this case that we cannot generate an embedding for a node that was not seen during training. We cannot transfer embeddings from one graph to another because for every graph, for every node, we have to directly learn learn that embedding in the training phase. And then another important drawback of the shallow encoders, as I said, like DeepWalk or Node2Vec, is that they do not incorporate node features, right? Many graphs have features properties attached to the nodes of the network, and these approaches do not naturally leverage them. So today we are going to talk about deep graph encoders. So we are going to discuss graph neural networks that are an example of deep graph encoders, where the idea is that this encoding of an embedding of a node V is a multi-layers of nonlinear transformations based on the graph structure. So basically now we'll really think about deep neural networks and how they are transforming information through multiple layers of nonlinear transforms to come up with the final embedding. And important to note that all these deep encoders can be combined also with node similarity functions in lecture 3. So we could say, I want to learn a deep encoder that encodes the similarity function, for example, the random walk similarity function that we used in the previous lectures. Or in this case, we can actually directly learn the encoder so that it is able to decode the node labels, which means we can actually directly train these models for node classification or any kind of graph prediction task. So intuitively, what we would like to do, or what we are going to do, is we are going to develop deep neural networks that on the left on the input will take graph as a structure together with properties, features of nodes and potentially of edges. We will send this through multiple layers of nonlinear transformations in the network so that at the end, in the output, we get, for example, node embeddings. We can also embed entire subgraphs. We can embed pairs of nodes and make various kinds of predictions in the end. And the good thing will be that we are able to train this in an end-to-end fashion. So from the labels on the right all the way down to the graph structure on the left. And this will be in some sense task agnostic, or it will be applicable to many different tasks. We'll be able to do node classification, we'll be able to do link prediction, we'll be able to do any kind of clustering community detection, as well as measure similarity or compatibility between different graphs or different subnetworks. So this will really allow us to be applied to any of these different tasks. So why is this interesting, or why is it hard, or why is it different from, let's say, classical machine learning or classical deep learning? If you think about classical deep learning toolbox, it is designed for simple data types. Essentially what traditional or current toolbox is really good at is we know how to process fixed size matrices, right? So basically I can resize every image and represent it as a fixed size matrix or as a fixed size grid graph. And I can also take, for example, text, speech, and think of it basically as a linear sequence, as a chain graph. And we know how to process that really, really well. So kind of the claim and motivation for this is that modern deep learning toolbox is designed for simple data types, meaning sequences, linear sequences, and fixed size grids. And of course, the question is, how can we generalize that? How can we apply deep learning, representation learning to more complex data types? And this is where graph neural networks come into play, because they allow us to apply representation learning to much more complex data types than just this kind of two very simple data types, meaning fixed size grids and linear sequences. And why is this hard? Why is this non-trivial to do? Is because networks have a lot of complexity, right? They have arbitrary size and they have complex topological structure, right? There is no spatial locality like in grids. This means that there is also no reference point or no fixed orderings on the nodes, which means that in a graph there is no top left or bottom right as there is in a grid. Or, there is no left and right as you can define in a text because it's a sequence. In a graph, there is no notion of a reference point. There is no notion of direction. And more interestingly, right, these graphs are often dynamic and have multiple multimodal features assigned to the nodes and edges of them. So this becomes very, very interesting because it really expands ways in which we can describe the data and in which we can represent the underlying domain and underlying data. Because not everything can be represented as a fixed size matrix or as a linear sequence. And there are, as I showed in the beginning, right, in the first lecture, there is a lot of domains, a lot of use cases where proper graphical representation is very, very important.